Talk, says Roop. Hello to you. Oh, flippin' heck. I haven't got another physics fact. I'm regretting doing this channel point reward already. Right, well, what physics fact can I come up with today? There was a nice one, actually, that I was going to put in a YouTube video that I never actually got around to. That was about the inventor of the LED. Did you know that white LEDs, I think they do a slightly different method of making them now, but originally the only way to make a white LED was to literally combine in a small space a red, green and a blue LED. One slight problem. Red LEDs have been around for donkey's years. Green LEDs are newer, but are certainly very, very mainstream. Which just left the blue LED. And did you know that the blue LED was only invented in 2014? Well, actually, yeah, this is very relevant at the moment because it's going smoothly, not very smoothly, where is it? Up there. So you might have noticed a new addition to the stream, a new temporary addition to the stream up in the top left corner there. I have finally plumped for... I've been in an hour about it for ages. I've been putting it off for ages. But I finally put the order in. Yeah, the new router has a blue LED and I've had to put tape over the front because it's quite bright. Even though I can set it in the software to reduce the brightness. I got like 8 layers of masking tape over it as well. So the brand new, beautiful router came out of the box today. Now, the new router, of course, is a broadband... is a fibre broadband router. But... yeah, there was something else I was going to say about blue LEDs. It just took them... yeah, it was the stumbling block to making blue LEDs, and the reason it took until 2014 to be able to finally pull it off was growing big enough crystals of gallium nitride. Because, you know, there's semiconductors in all LEDs, and you can't just make a particular colour. It's not like you add, 2 parts of this and 3 parts of that and you get yellow. LEDs don't quite work like that. You've got to have a crystal that you grow very slowly and uniformly and under controlled conditions with as few impurities in it as possible, or at least only the impurities you want to be in there, because there's deliberate impurities. Gallium nitride, it will mean that there'll be some gallium impurities and some nitrogen atom. Now we're fumbling the physics here. Yeah, the crystal generally will be what they call doped, which is not necessarily a bad thing. It's a bad thing in athletics. In the Olympics, it's not a bad thing necessarily in science in general. So doping is the process where you're deliberately introducing a very, very small amount of impurity to something, to a crystal normally, whether it's a laser crystal or an LED crystal or any semiconductor crystal. You're deliberately introducing a small amount of impurity to change the properties of it. And presumably, again, this is going into more the engineering of it, which I don't know so much about, but it was hard. It was hard to make this stuff. And I presume that to experiment on it to see if it even worked in order to make an LED, you'd need to grow at least enough to make a test LED. This is the same issue, I suppose, on a different scale, in a completely different field. I guess it is the stumbling block for quantum computing, because there's a huge amount of research being done and a huge amount of progress being made in quantum computing, but you can only build very small ones because it's very expensive to build them, and it's very hard to keep them under the conditions they need to be kept in. So, I mean, again, once you've grown a crystal, it tends to be there. You've grown it, it's done. A quantum computer doesn't work like that. When you build it, you have to keep it under very, very controlled conditions, or if the quantum state of it breaks down, well, it's not a quantum computer anymore. It's like a very expensive doorstop, I guess. It's like, so it's not quite the same. Once you've made the crystal, you've made it. As long as you don't smash it or allow massive impurities to get into it somehow, or scratch the surface of it, it's there. It's a crystal. It exists, and it will continue to be a crystal. But obviously then it has to be big enough to actually work on and attach to an electric circuit and experiment on and sort of tune and I didn't say you couldn't tune it, but you can't just, like I say, it's not like 2 parts of one thing, 4 parts of another thing, and a little sprinkle of this, and you've got blue. Not necessarily, because you've only got certain elements to work with. Yes, there are a lot of elements in the periodic table. There are a lot of elements available on Earth. You don't necessarily need very much of it to make an LED, so yeah, it's rare, but rarity shouldn't be an issue if you only need a very small amount of it. Gold's rare, but you see plenty of gold around. I know less and less, and that's why people are trying to reclaim it. Yeah, but I'm just saying, all of you have seen it. It exists in enough quantities that all of you have at least seen a piece of gold at some point in your life, I'm sure. Even if it's just like a little gold coating on something, you know, it's not so rare that you've never ever seen it. Same with things like gallium and all that sort of stuff, you know. It's but growing it, I guess, was hard because that's the thing. Crystals grow very slowly. There are various methods by which to do it, but the key is, right, anybody who's had a crystal kit to grow your own crystal, you know how slow they grow, and that's in the open air with a box you can buy yourself. This stuff has to be done in, like, a vacuum, with vapor deposition probably, and maybe that's it. Maybe even under the most controlled conditions they had at the time, it just never assembled correctly. Because, I mean, you're playing with atoms when you're trying to grow a crystal. You're trying to get it to grow in an orderly form. It's like, I don't know, like playing with Lego and just trying to drop them very carefully so that they landed on each other and click together. And hoping to build a house out of them, but you're only able to drop them because you can't actually get down there and press them together, because let's pretend that these Lego bricks are more like atoms. If you actually try to put your hand in there, it would just blow itself to bits because your hands are full of atoms as well. The analogy is going to break down somewhere. All analogies break down somewhere. No analogy is perfect. Yeah, let's pretend that it's like a really, really clumsy person, the clumsiest person in the world times 1,000, working with Lego bricks, and you can't put them together piece by piece yourself with your own hands. You have to drop them from a height and hope they land in the places you want them to, and that's hard. Most crystals kind of self-organize, but unless you get the conditions perfectly correct, they're going to self-organize how they like. It's I can't think of an analogy for that, but the atoms are gonna go where they want to. You've got to make the conditions. Oh, that's quite good. Remember this one. That's quite a good explanation. The atoms will go where they want to go. You actually have very little control in that. What you do have control over is that you can make the conditions more favourable to them doing what you want them to do, but you can never actually force them to do it. They've not got a conscience, or a consciousness, or a conscience. You can't just speak to them nicely and hope they'll do what you want. You just have to make the conditions. And anyway, right, I'm going into this too much, and more than my experience will probably tell me.